Hello and welcome back to GCSE Science Simplified, the podcast that takes big science ideas and makes them make sense. Today's question is a strange one. Why does a straw look bent in a glass of water? Why do swimming pools look shallower than they really are? And how do glasses, cameras, and even our eyes rely on the same idea? The answer? Refraction. And by the end of this episode, you'll understand it well enough to explain it in a classroom, exam, or in real life. Picture this. You're at a cafe. You look down at your drink, and the straw looks like it's snapped in half at the surface of the liquid. It hasn't. Light has changed direction. That bending happens at a boundary, when light moves from air into water. Whenever a wave crosses from one medium to another and changes speed, its direction usually changes too. That change in direction is what we call refraction. Here's the key idea. Refraction happens because wave changes speed. Light travels at different speeds in different materials. It moves fastest in air, slower in water, and slower still in glass. When light crosses a boundary at an angle and its speed changes, it bends. Importantly, the frequency of the wave does not change. The source hasn't changed, so the frequency stays the same. Instead, it's the wavelength that changes to match the new speed. It's this relationship. Speed equals the frequency times the wavelength. It's why bending happens. Now let's step into the classroom. Imagine the classic refraction practical with a rectangular glass block. You shine a ray of light onto the block at an angle, draw around it and trace the path of the ray. What you always see is this. The ray bends towards the normal as it enters the glass. It travels straight through the block, then it bends away from the normal as it exits back into air. Because the block has parallel sides, the ray comes out parallel to the original ray, just shifted sideways. This practical isn't about neat diagrams. It's about showing that light slows down in glass and speeds up again in air. Of course, this experiment isn't perfect. Pencil lines are thick. Normal lines might not be exactly 90 degrees, and it's easy to misjudge the angle of the ray. That's why repeating measurements and using thin, sharp rays improve accuracy. In exams, it's important to recognise the results are estimates, not exact values. Not all materials behave in the same way. Some transmit waves, like clear glass. Others absorb them, like dark sunglasses. Some reflect waves, like mirrors. And this behaviour can depend on wavelength. That's why glass prisms separate white light into colours. Each wavelength bends by a slightly different amount. It's also why infrared and ultraviolet behave differently in materials compared to visible light. Now let's switch waves from light to sound. Sound waves can also cross boundaries, like moving from air into water. Just like light, the frequency of sound stays the same when it enters a new medium. But the speed of sound changes. Sound travels much faster in water than in air. So what changes instead? The wavelength. Higher speed, same frequency, longer wavelength. This relationship explains why sound bends and behaves differently underwater, and why sonar and ultrasound work. Refraction isn't just theory. It's how glasses correct your vision, how camera lens focuses light, and how fibre optic cables transmit information. Even your eyes rely on refraction. The lens bends light so it focuses precisely on your retina. Without refraction, clear vision wouldn't be possible. So remember this. Refraction is about changing speed at a boundary. Direction changes, wavelength changes, but frequency stays the same. Whether it's a bent straw, a glass block experiment, or sound moving underwater, the physics is the same. That's refraction. GCSE Science Simplified.